Hello everyone, on behalf of the team, I'm going to present our work, Best Practices for Two-Body Pose Forecasting. The objective of human pose forecasting is to forecast future movements by analyzing past data. Currently, most research has been done on single-body scenario. However, we address a scenario involving two agents in interaction. Further, we put an additional focus on extreme interactions. There is currently only one publicly available XPi dataset that showcases a high degree of interaction between two actors, performing Lindy Hop dancing movements. This dataset represents the bodies of both actors through 3D key points of skeletons. In this study, we thoroughly examine the established practices employed in single-body pose forecasting and extend our analysis to collaborative human pose forecasting. During the upcoming slides, we will present and evaluate these practices, using a checkmark to indicate the ones we adopt and a cross to signify those we omit. To begin with, we utilize frequency representations by applying the discrete cosine transformation to convert the input into the frequency domain. The discrete cosine transform is known for capturing smooth movements through frequencies and has demonstrated excellent performance. Next, we delve into the concept of hierarchies, where neighboring nodes are combined to generate multi-scale representations. Although this approach has demonstrated excellent performance in single-body pose forecasting, it falls short in the case of two bodies. This discrepancy may be attributed to the fact that the aggregation of nodes from multiple agents fails to consider the interactive aspect. Thirdly, graph convolutional networks, GCNs, are regarded as an ideal choice for representing 3D skeleton data. In our approach, we employ a separable and spatial temporal formulation of the graph, allowing us to capture the interaction between the body joints. This is achieved by employing a learnable spatial and temporal adjacency matrix. Furthermore, we conducted experiments using a graph attention network, GAT, with multi-head attention to enhance the interactive aspect. However, our findings indicate that although it increases the computational cost, it does not yield significant performance improvements. Lastly, we incorporate a multi-layer perceptron, MLP, in the decoder of our architecture. It is generally beneficial to constrain the distribution from which parameters are sampled during the learning process, as failing to do so can lead to issues such as exploding or vanishing gradients. While shallow networks may not encounter significant problems in this regard, deep models require specific initialization techniques to address these challenges. However, it is worth noting that no specific initialization method has been proposed or established for graph convolutional networks, GCNs. Hence, we propose a novel initialization approach for graph convolutional networks, GCNs. Our method involves initializing separate spatial and temporal matrices. Each is initialized according to a uniform distribution. The bounds of this distribution are determined by the number of graph nodes for the spatial part and the timeframes for the temporal part. We assume that the parameters of these matrices are independent, identically distributed, uniformly distributed, and have a mean of 0. This initialization strategy promotes better gradient flow and alleviates issues associated with deep GCN architectures. Below are the formulas for initializing the spatial and temporal adjacency matrices. Here, NT represents the number of timeframes, NV denotes the number of nodes, and L indicates the layer number. This straightforward architecture consistently achieves state-of-the-art performance when compared to other models. We evaluate the performance of our model using the mean per joint position error. This metric measures the average error between the ground truth and the predicted joint positions at a specific future timeframe t. The results highlighted in red in the table represent the previous state-of-the-art performance. On the other hand, the results highlighted in yellow correspond to the performance achieved by using only the separable and learnable graph convolutional network, GCN, which we consider the baseline model. When employing our new initialization formulation, we observe notable improvements in the results, particularly in long-term predictions. By incorporating the frequency encoding on top of the baseline model, we observe significant and substantial improvements in the results. Replacing the temporal convolutional network, TCN, with a fully connected layer yields further improvements in the results. Lastly, when combining all of the aforementioned practices, including the new initialization formulation, frequency encoding, and utilizing a fully connected layer instead of a TCN, we observe that the model surpasses all other combinations in terms of performance. In our qualitative evaluation, we present visual results and conduct a comparison with the state-of-the-art approach. It is evident from the green square in the comparison that our approach exhibits greater precision, smoother motion, and avoids issues such as the scaling of the skeleton, which can be observed in the red square representing the state-of-the-art method. Furthermore, our approach demonstrates a reduced deviation from the ground truth compared to the other model. This indicates that our method better captures the desired poses and movements, resulting in a closer alignment with the ground truth data. Even in the case of extreme actions, our model excels at generating smooth and natural motion, whereas the previous method produces unnatural motions with noticeable deviations from the ground truth. Our model's ability to handle extreme actions and maintain the smoothness and naturalness of the predicted motion showcases its robustness and effectiveness in capturing complex movements. The link to our project and code can be found by scanning the QR code. Thank you very much for your attention.